Okay, let's jump right into this explainer. Picture this. You're cruising down the highway in your brand new EV. The ride is smooth, it's quiet. But deep inside the chassis, specifically inside the battery's brain, something snaps. A rogue cosmic ray hits, or maybe there's a microscopic manufacturing flaw. In a fraction of a millisecond, the software's logic just freezes. What do? Well, the truth is, you don't do anything. You can't. The car literally has to save itself.
It's a terrifying thought, right? What actually happens when a high-voltage system goes rogue at 70 miles an hour? This is exactly what automotive engineers lose sleep over, and it's why they don't just write good code, they build an absolute digital fortress under the hood to stop a catastrophe before you even see a flicker on your dashboard. Today, we're taking an exclusive look inside that fortress.
Looking at the complete functional safety diagnostic list for EV batteries, we're zooming in on the fourth dimension today, the software algorithm and control logic layer. Specifically, fault 405, the ultimate failsafe, the code engineers both fear and revere, P0A0B. Basically, it's an internal software logic fault. It gets thrown the exact split second the microcontroller or its operating system starts acting unpredictable and loses the ability to sustain normal logic. When P0A0B hits, the system's trust in itself drops to absolute zero.
To really understand this engineering marvel, we're going to systematically unpack it across 5 dimensions: root causes, the 3-layer architecture, design prevention, zero-defect manufacturing, and finally, verification.
Let's kick things off with Section 1, root causes, the invisible killers attempting to crash the system.
So what actually pushes the system to the brink? Well, we've got 4 main villains here. First up, real-time operating system deadlocks. This is like 2 software threads wrestling over the exact same resource. The program counter literally runs away, and critical deadlines get missed. Then you have your classic runtime errors, like stack overflows, which can completely sever control of the high-voltage relays. Third is EMI, or electromagnetic interference. High-voltage switching creates so much electrical noise it can literally cause a physical bit flip in the memory. And lastly, ESD, electrostatic discharge. Just a tiny static shock on the factory floor can leave dormant damage that decides to jam the hardware years down the road. Moving on to Section 2, architecture. Here is how we build a 3-layer defense to guard the core, using ASIL-C and D hardware. To fight off those threats, engineers use a dual-core lockstep architecture. It's basically 2 independent accountants doing the exact same math at the exact same time. If they disagree by even a fraction, boom, the alarm goes off. This fits beautifully into an EGAS 3-level safety model. Level 1 is out there driving the car, executing core functions and relaying states. Level 2 is the strict supervisor, constantly calculating logic residuals and comparing the dual cores. And Level 3? That's the quiet custodian in the background, continuously running March-C algorithms to check memory health and verifying ROM integrity. But hey, what if the main brain itself just completely goes rogue? That is where the absolute ultimate defense steps in. An independent chip entirely outside the main processor called the System Basis Chip, or SBC. Think of it like a dead man's switch on a train. It acts as a window watchdog, relentlessly firing complex challenge questions at the main processor and demanding the right answer back within a very precise time window. And the magic number here is 2 milliseconds. If the main brain locks up and misses its window to answer the SBC's challenge, the SBC assumes a total catastrophic failure. It completely bypasses all the normal software logic and physically severs the high-voltage power in under 2 milliseconds. It is a rigid, unforgiving, hard shutdown designed to keep you safe. Next up is Section 4. Actually, scratch that, Section 3. Design, blocking at the source through DFMEA critical design prevention. Because a logic failure scores an 8, the absolute highest severity rating in engineering, you can't just react to it. You have to design the flaw out before a single line of code is compiled. The rules are intense. We're talking 100% mandatory MISRA-C compliance. They use aggressive static analysis to guarantee 0 undefined behaviors. No infinite loops at all. They also use strict hardware partitioning so tasks literally cannot overwrite each other. But my absolute favorite detail? Decoupling capacitors. If the 12-volt battery suddenly drops, these little reserve tanks buy the system exactly 50 milliseconds of emergency power. That's just enough time to safely save data, run a checksum, and power down gracefully without corrupting everything. All right, Section 4, process. zero defect manufacturing, or perfecting the forge through PFMEA.
Because, let's be real, perfect software means nothing if the physical circuit board gets fried on the assembly line. To stop those invisible factory killers we talked about, the manufacturing process requires 100% live monitoring. Workers and machines have their grounding resistance monitored constantly to stop static shocks. They use 3D optical scanners to catch microscopic cold welds. Casings are rigorously tested to ensure they are airtight and block out EMI. And to stop human error during software loading, they use a POCA-Yoke dataset lock. It physically restricts operators from manually picking a software version, meaning accidentally flashing the wrong file into your EV is literally impossible.
Finally, we arrive at Section 5, verification, the ultimate test, driven by DVP and R million-mile validation. Before any of this tech is ever allowed on public roads, it goes through an absolute trial by fire. Imagine a simulation where the car is running flawlessly. Suddenly, engineers deliberately inject a single event upset. They artificially flip just one bit of SRAM data to mimic a random cosmic ray strike. In less than 100 milliseconds, the background March C algorithm has to detect the anomaly, cross-check it, and lock the system into a safe state by throwing that P0A0B code.
And they don't stop there. Using hardware-in-the-loop simulators, these engineers get malicious. They intentionally inject infinite deadlocks straight into the highest priority tasks. They crash the car's brain on purpose, just to prove that our hero, the external SBC watchdog chip, will spot them as deadline and ruthlessly cut the power inside its rigid 2-millisecond window.
What is so brilliant about this whole architecture is how adaptive it is. Not every glitch demands a full shutdown. If it's just a random, transient software hiccup, the system triggers a warm reset and completely heals itself in under 100 milliseconds. You honestly wouldn't even feel it while driving. But if that reset fails 3 times in a row, the system knows it's a permanent fundamental error. It ruthlessly throws a hard lock and shuts down the high-voltage system immediately, ensuring you never drive a compromised vehicle.
So, after peeling back the layers of this digital fortress, from isolating the root causes to those 2-millisecond hardware shutdowns and the intense verification tests, it really changes your perspective, doesn't it? Next time you fire up your EV and seamlessly merge onto the highway, just ask yourself, how many microscopic, invisible software disasters did your car just silently detect, isolate, and completely neutralize in the blink of an eye, all while you were just trying to find a good song?